let's get started here. Let's just talk about where we are at in terms of our lecture. We have something called KSP. This stands for the solubility product constant. Okay, so what you're looking for here is a solid, okay, a solid that is sparingly soluble. Okay, so there's a whole list on page, on page, whatever the page is, but there's a whole list of sparingly soluble solids. So AgCl is one of them. There's a whole list, like I mentioned. Where are we at here? There's a whole list of sparingly soluble solids that's on page 12. So for AgCl, this one is going to be, I think, 1.6 times 10 to the minus 10. So I'll give you that. I'll give you that on the exam. This is a solid that can go back, okay, go back into its component ions. In this case, that's Ag plus and Cl minus. So let's just complete this. So some of it that goes back, we're going to call it plus S. This S stands for solubility. Plus S, plus S. This is 1S because there's one Ag plus. This is 1S because there's one Cl minus. Let me ask you this question. What's the total charge on the product side? 0. Plus and minus is 0. What's the total charge on the reactant side? 0. Okay, so the charges have to be balanced. Let's just continue on with what we'll have to do for these types of problems. So the KSP is going to be products over reactants. Like I said, I'll give you the KSP. Okay, so this S will go here. Okay, this S will go there. Okay, so 1.6 times 10 to the minus 10 equals S times S. S times S, and that is S squared. Okay, so here, once again, the S stands for solubility. How much of the solid goes back, dissolves back into the ions? So to get our solubility, 1.6 times 10 to the minus 10, we'll square root it. And let me just give you that so that we can save some time, calculator time. This is, actually it's right here, 1.26 times 10 to the minus 5. Right, so this is what you'll have to do for your KSP. Right, so the solubility of Ag plus is going to be 1.26 times 10 to the minus 5 molar. Okay, so make sure we are very aware of our units here, and the units here are going to be molarity, which is moles over liter. And the S solubility of Cl minus will be the same, 1.26 times 10 to the minus 5 molarity. Like I said on the exam, if I were to make a comment, my remark is that students are not putting in their units. Okay, so let's not do that. Let's put in our units. So that's how we do these types of problems. Now I want to introduce to you something called Q. Okay, Q, and this Q stands for reaction quotient. So we always use Q to compare to K. Okay, so let me just write this here. It's kind of a long sentence, but let's write it. We use Q to compare to K, but actually we use Q in this case to compare to KSP. And this tells us whether the reaction is at equilibrium or not. This tells whether the reaction is at equilibrium or not. And if it is not at equilibrium, which way will it shift to get to equilibrium? So we will use Q and compare it to KSP. So there's three things that could happen. Okay, one is that Q, we're going to compare Q with KSP. Now in this situation, I want you to put Q first. Okay, put Q first. Okay, there's three things that could happen. The Q can be greater than KSP, the Q can equal KSP, and the Q can be less than KSP. So if the Q is greater than KSP, okay, where do the alligator jaws point? Okay, do they point to the solid side or do they point to the side of dissolved ions? Okay, if Q, put Q first, if Q is greater than KSP, then the equilibrium favors the solid, okay, also known as precipitate. Okay, you know what the word precipitate means? What does precipitate mean? Means solid. Okay. So if Q is greater than KSP, which is the solubility product constant, we will form a precipitate. Okay. Here, PPT means precipitate. Okay, what happens if Q is less than KSP? Where do the alligator jaws point? They're pointing to the side of no solid. They're pointing to the side of water, and dissolved in that water are these ions. So here, it's no precipitate. Okay, check where the alligator jaws go. No precipitate. Okay, it's just the ions dissolved in water. And then Q is equal to KSP. This is what we will call a saturated solution. It's not really forming a precipitate, but whatever the solid is in there, it's on the cusp. Okay, it's on the cusp of giving you a precipitate. So just enough solute in the solvent, and anything more, and okay, you'll get a precipitate. So this is called a saturated solution. All right, so these are the three scenarios. So let's go over a problem that we will see on the exam where we will determine whether we will get a precipitate or not. Before we do a problem, just remember one more time, put Q first. Okay, that's point number one. Second thing is KSP. Okay, the solid is always on the reactant side. Okay, these are all equilibriums. Yes. Okay, if you want to do the gator rule. Okay, this is how I learned it. So gator rule, alligator rule. Okay, if you want to do something else, I think the book has it a different way. All right, so put Q first if you want to use the gator rule. All right. Now let's do a problem. I think you'll definitely you'll see a type of problem on the exam. So this is a good practice problem for the test. Before we do that, just want to give you, here's a list of all the sparingly soluble solids. So I'll give you the KSP, don't worry about it. And then here's a flow chart of how we solve some of these problems. The solubility, don't forget, is S. Okay, and then the solubility actually can be in two forms. It could be in molar solubility or it can be in grams over liters. So this is just for your reference. All right, I'll give you the KSP. Again, KSP, sparingly soluble solids. Okay, add a specific. Again, KSP, sparingly soluble solids. Okay, at a specific temperature. Okay, before we do the Q problems, let's do some KSP problems. So page 14 is the reaction quotient problems. Page 13 are just some KSP problems that we'll do. So we'll do that here. Wait, where are we at here?
Which is on page 11.
Oh, wait. Page... Oh, I skipped page 11, right? Did I? 12, 13, 14...
Yeah, there's a table on page 11, but I think it's worked out.
15, 16... Yeah, okay. Let's do this problem here. I skipped page 11. All right. Back on track. Sorry about that. Okay. All right, let's do a reaction quotient problem. Okay. All right, so follow along with me. Let's do this together here. All right, so something like this will be on the exam. This is page 11 of our notes. All right, so if 2 milliliters of a 0.2 molar NaOH are added to 1 liter of 0.1 molar calcium chloride, will a precipitate occur? Okay, so on the exam, will a precipitate occur? The question is yes or no. So one thing here is this sodium hydroxide is actually sodium ion and hydroxide ion. And then this calcium chloride is calcium ion and chloride ion. So sodium hydroxide in water is sodium ion and hydroxide ion. Calcium chloride in water is calcium ion and chloride ion. Okay, so this 2 mils, okay, is nothing more than 0.002 liters. 1, 2, 3, okay? And 1 liter is just 1 liter. All right, so when you mix this NaOH, which is a source of sodium ion and hydroxide ion, with the calcium chloride, which is a source of calcium ion and chloride ion, what happens is that the sodium will go with chloride and give you NaCl. But if you remember the solubility table way back in Gen Chem 1, sodium chloride actually dissolves in water. Okay? But, okay, calcium ion and hydroxide ion does not dissolve in water, okay, when you mix these two. Okay, so calcium hydroxide is our sparingly soluble solid. Okay. And it has a KSP. I'll give you this on the test. Okay, so it has a KSP of 8 times 10 to the minus 6. And what do I need to do with this equation here? All equations, what do we need to do? Okay, balance it, so it will be a 2 here. Okay. So like we said, in these types of problems, some of it will go back. Okay, some of it will go back. So this will be plus s, and this will be not plus s, but very good, plus 2s. Okay. All right, so we will continue this problem like we did our problem at the very beginning of class. KSP is equal to calcium ion plus hydroxide ion. Okay. All right, why did I square it? Okay, this is why I squared it, so make sure you do that on the exam. So the calcium ion here is S. The calcium ion here is 2S. And I'll give you the KSP. It's 8 times 10 to the minus 6 equals S times 2S squared. Okay? All right, so here we're not solving for solubility S. Okay? What we're going to do here is answer the question. Okay, now we'll stop here and answer this question. Will it precipitate form? Okay, we have our source of OH minus. We have our source of calcium. Is this enough? Is this volume and concentration of OH minus enough when combined with this volume and this concentration of calcium ion? Are these two have enough power to precipitate calcium hydroxide? So what we do now is we will calculate the concentration after mixing. Okay. This is what I want you to do on the exam. So calculate the concentration after mixing. Right, first we will do the OH minus. Okay, we have 0.002 liters times 0.2 molar. Okay, divided by what's our total volume? 1.002. Okay, the liters cancel. So I'm just going to go ahead and write down that number for you guys. It's 0.0004, 3 zeros. No, it's we're calculating the concentration of the OH when you mix this with this. So you're going to take 0.002 liters times the 0.2 molar of OH divided by the total volume. The total volume is 1.002. Okay. Right, so that is the concentration of OH minus. We'll plug that in here and see if that's enough OH to precipitate or not. Let's do the same thing for the calcium ion. Let's do that in this color. So we have 1 liter times 0.100 molar. Okay, what is our total volume? It's the same, 1.002. The liters cancel. And I'll go ahead and give you that number on my calculator. Let's save some time here. 0.0998 molar. That's calcium ion, and let's put that in here, okay? Alright, so in this type of problem, we're asking, will it precipitate or not? So now we will plug those numbers in. So we have 8 times 10 to the minus 6, which is the KSP. I'll give you that on the exam. Equals the S in the calcium ion. When we mix these two, the final concentration will be 0.0998. And then after we mix these two, the final concentration of OH minus would be 0.0004. Let's plug that in here as our S times 2 and then square it. All right, I do this on my calculator. 2 times 0.0004 is 0.0008. Square it times 0.0998. And I am getting this. I'm getting 6 times 10 to the minus 8. So something is not right. Okay. So these concentrations do not equal KSP. So we're not at equilibrium. Where are we at? Which way will it go to get to equilibrium? Okay, so in this case, let's compare Q and KSP. Q is 6 times 10 to the minus 8. Okay, I want you to put Q first. And KSP is 8 times 10 to the minus 6. Okay, so which is bigger? Okay, 8 times 10 to the minus 6 is bigger than 6 times 10 to the minus 8. It's about 100-fold bigger. So which way do the alligator jaws point? To the right. So will we get a precipitate here? Yes or no? No, no. Okay, no. So the correct answer here is no. Okay, so can we do something like this on the exam? Okay. This is not enough to give you a precipitate. Okay? This is not enough OH minus source. This is not enough calcium ion source to precipitate calcium hydroxide. Okay, we have to go through all these things. All right, so it will not form a precipitate, you're right. All right, are we good in doing this on the test? Okay, we'll do a couple of more on Thursday as well. All right, we'll do one more actually. All right, so that's page 11, page 12. Like I said before, I'll give you these values, the constants. You can look at this just as a guide to how we solve these types of problems. And now let's go ahead and do page 13 here. All right, the solubility of calcium sulfate is found experimentally to be 0.67 grams per liter. Calculate the value of KSP for calcium sulfate. Okay. All right, so like we did before calcium sulfate, do we know the equation? The calcium sulfate is this. Okay. It's calcium ion and sulfate ion. And the solubility, S, was 0.67 grams per liter. But here, in these KSP problems, we have to use moles over liter. Alright, so like we said, some of it's going to go this way. So it's going to be plus S and then plus S. Alright, KSP is equal to calcium ion and sulfate ion. But remember, this brackets is concentration. Okay. So what we need to do here to calculate the KSP is convert these grams per liter to moles over liter. So we want to calculate the KSP. Usually, 99% of the problems that I'll give you the KSP, but in this case, we have to calculate it. But we can calculate it from the solubility they give us as 0.67 grams per liter. So all we got to do is convert it to moles over liter. And then plug it back in. So 1 mole of calcium sulfate is 136.19 grams of calcium sulfate. Okay, the grams cancel, and I'm getting about 0.00492 moles over liter. So all we got to do is plug that into here, because that's S, it's a 1-to-1, and plug it in here. So the KSP, as a result, is going to equal to 0.00492 times 0.00492. And I'm getting 2.42 times 10 to the minus 5. Okay, so that is our KSP of calcium sulfate. So like I said, this is a twist on a problem, because usually, at least for my exam, I'll give you the KSP. In this problem, they're having you calculate the KSP, but they give you the solubility in grams over liter. All right, what is the solubility of silver chloride? We already did that. It's on, actually it's given to us on page 10 of our notes. Yeah, page 10, so check out page 10. And then, something that's nice to see here, all the different relationships. So AgCl is in a 1-to-1, so it's X to X, S to S. Okay, and these are the different KSPs. Okay, we did this one in class, and then we did this one in class. Okay, and these are all different sparingly soluble solids. Okay, remember we're using S here for solubility. Alright, so you can look that up in the course of your studying. Let's move on to page 14 here. Alright, so will a precipitate form if exactly 200 mLs of 0.0040 barium chloride are added exactly to 600 mLs of 0.0080 molar potassium sulfate? Alright, so the KSP of barium sulfate is 1.1 times 10 to the minus 10. So another one that's going to be very similar to what you'll find on the exam. So this barium chloride is barium ion and chloride ion. And this potassium sulfate is K plus and SO4 minus 2. Okay. So when these two react, they'll give you barium sulfate, which is sparingly soluble. Okay, a little bit soluble. And the KSP is 1.1 times 10 to the minus 10. So the first thing we'll do is write our equation. Like I said, the KSP will be 1.1 times 10 to the minus 10. Alright, some of it will go back this way. This is going to be plus S. And some of it will go back this way, like I said before, that's plus S. Alright, so let's continue this problem here. KSP is going to equal to concentration of barium ion times the concentration of the sulfate ion. Alright. And before we move forward, the question is, will a precipitate form? Let's figure out the concentrations of each of these after mixing. Alright, shall we do that? Okay, we'll first do the barium ion. which is 200 mLs times 0.004 big M. Okay, what's our total volume? Okay, I'm seeing a total volume of 800 mLs. Is that right? Yes? Okay, good. Thank you. And the mils cancel, giving us molar. And on my calculator, I'm getting 0.001 big M. All right, let's do the same thing for sulfate, SO4 minus 2. Here we have 600 mLs times 0.0080 big M. Total volume 800, correct, Bailey? Yes. Okay, the mils cancel. 600 times 0.008 divided by 800, I am getting 0.006 big M. All right, let's plug everything in now. KSP is 1.1 times 10 to the minus 10. Okay, barium ion is plus S, but we will use 0.001. And SO4 minus 2 is 0.006. Okay, so there are no units in the KSP. So question, are there units for capital K? No. Okay, there's no units. Okay, no units for pH, no units for K. All right, I see an issue here. 1.1 times 10 to the minus 10 equals this times this. 0.001 times 0.006 is 6.0 times 10 to the minus 6. Something is not right. They don't equal to each other. This doesn't equal to the KSP. So we're not at equilibrium. Which way will the reaction shift to get to its right place? By right place, I mean equilibrium. Okay, so we're going to put Q first. And then K. What is Q? It's going to be 6.0 times 10 to the minus 6. KSP is 1.1 times 10 to the minus 10. Okay, which is bigger? My 6.0 times 10 to the minus 6 is bigger. And which way do the alligator jaws point? Okay, to the side that has a precipitate or no precipitate. Okay, to the side that has a precipitate. So question, will a precipitate form if you add this proportion of barium chloride, source of barium, and this proportion of potassium sulfate, source of sulfate? Will you get a precipitate of barium sulfate, yes or no? Okay, the answer is yes. So this is what you should do on the exam or quiz or whatever it may be. Okay. All right, are you comfortable doing this on the test? All right, finally, the last couple of wrap-up points here is the common ion effect. All right, so one thing, I don't know if you remember the very beginning of this chapter, I wanted you to link common ion with suppression of ionization. Okay. It also means the suppression of solubility, or it decreases the solubility. Okay. I'm going to say decreases S, and here the S stands for solubility. All right, so let's see how the common ion affects KSP. All right, so another thing that will be on the exam, and that's illustrated on page 15 of our notes. Okay, page 15 and 16. So how does this common ion affect KSP? Okay, suppression of ionization decreases solubility S. Let's see what all this means on page 15. All right, so something very similar on the exam, so let's do this together. Calculate the solubility in molarity M of AgBr in pure water and part B is a twist. Okay, in not pure water solvent, but this solvent, 0.001 molar sodium bromide. All right, I'll give you the KSP for this. I'll give it to you at 7.7 times 10 to the minus 13. Okay, I'll give you that. So calculating the solubility in pure water is a problem we've done. Okay, we did it with AgCl, we did it with calcium phosphate last week, and now we'll do it with AgBr. Okay. First thing, we're going to write our equation. Or the KSP, I'll give you that, and 7.7 times 10 to the minus 13. All right, some of it will go back this way. This is plus S. This is plus S. Plug it into the KSP. Okay, this S goes here for AgBr. This S goes here for Br minus. The KSP is something I'll give you as 7.7 times 10 to the minus 13. Okay, this S times this S is S squared. So S here is going to be the square root of 7.7 times 10 to the minus 13. And then on my calculator, I am getting the solubility to be 8.8 times 10 to the minus 7. Are there units here for solubility? Yes. Okay, solubility is in units of molarity. It can also be grams per liter, but this is molarity. So just to complete this, okay, how much of this goes back? In 1 liter, you'll get 8.8 times 10 to the minus 7 moles. How much of it goes back? Okay, in 1 liter, you'll have 8.8 times 10 to the minus 7 moles over liter for Br minus. All right, this is something that's hopefully you're becoming comfortable with. But now let's do the thing here, something different. And now the solubility is not in water. Okay, the solubility is in NaBr. So what is really NaBr? Okay, NaBr is Na plus sodium ion and Br minus. Those are the ions that make up NaBr. But in water, it's Na plus and Br minus. So part B here. Okay, let's write the same thing. All right, now this is different here because what do we have? Okay, some of it will go this side. This will remain plus S. But the Br minus will also be S. But what is the second source of the Br minus? The second source of the Br minus is not water. It's in part A, pure water. The second source of the Br minus in part B is the actual 0.010 sodium bromide. So this is actually going to be S plus 0.0100 molar. Okay? So question for you guys, what is the common ion here? It's not Ag plus. What's the common ion? Br minus. Is that what you said, Antoinette? Yes? You said that good. Common ion is Br minus. Okay? Okay, there's two sources of Br minus. Can you tell me one? What's one source of Br minus?
NABR.
Okay, good. One of them is NABR. What's the second source, Bailey?
It would be AGBR. Or
The AGBR going back is the second source. Okay? So what are the two sources of Br minus? The first source is the actual KSP, okay, going back, AGBR. What's the second source? Okay, the second source is the common ion. Okay. All right, so what's the difference between part A and part B? Common ion, yes. Okay. All right, now we're going to do everything as before. Okay, since there's no units, the units are going to be molar, but I'll add the units later. All right, so now we have this situation. So I want you to do this. We can assume S is small, okay? Okay, when we assume S is small, we're going to say S plus 0.0100 is about 0.0100 m, okay? So this makes things easier so we don't have to do the quadratic. So this is what I want you to do on the exam for this type of problem, okay? For this type of problem. So from assuming that the S is small, that most of the Br minus is coming from the NABR, or Br minus. So now the solubility will be 7.7 times 10 to the minus 13 divided by 0.0100. This is going to equal to S. And I am getting here S to equal 7.7 times 10 to the minus 11. Don't forget big M here. All right, so the solubility, let's just compare the solubilities here. Okay, in pure water, 8.8 times 10 to the minus 7. In the presence of the common ion, 7.7 times 10 to the minus 11. Okay, yes, the common ion will decrease solubility. This has decreased from 10 to the minus 7 to 10 to the minus 11. Okay. Okay, the common ion, in this case Br minus, okay, it has decreased solubility. Suppression of ionization, decreasing solubility. This is what the common ion does. All right, so the solubility of Ag plus is 7.7 times 10 to the minus 11 molar. The solubility of Br minus is 7.7 times 10 to the minus 11 molar plus 0.0100. And that's really just 0.0100. Okay, 10 to the minus 11 plus 0.01 is 0.01. All right. All right, and you can see most of the Br minus has come in the form of the 0.01 Br minus, the solvent here, the new solvent with the common ion. Right, so can we do this on the exam, something like this? All right, so let's prepare ourselves to do something where we do a KSP problem, calculate the solubility. But in this case, we're going to calculate the solubility as before, but in the presence of common ion. All right, page 16, we'll do another one like this. Calculate the solubility of silver chloride in grams per liter in a 6.5 times 10 to the minus 3 molar silver nitrate solution. All right, so what is the KSP of silver chloride? Let's check that out. The KSP of silver chloride is, hold on, I'll go find it. KSP of silver chloride is, I'll give you this on the exam, but 1.6 times 10 to the minus 10. All right, some of it will go back, okay? By the way, we have it in silver nitrate. What is silver nitrate? Anybody here from Chem 1? You never forget anything from Chem 1, right? What is nitrate ion? You're rolling your eyes at me. What is the nitrate ion?
Is it NO3 to the negative?
Correct. See, she didn't forget.
When my eyes, I was looking inside with the thing. Please don't call me. Please don't call on me.
I'm going to call on you. All right, so she's correct. Silver nitrate is AgNO3. All right, so silver nitrate, do you remember all nitrates are soluble? Okay, if you had me in chemistry, nobody here had me in Chem 1 last year, so you had me in the lab. All nitrates are soluble. Okay, so all nitrates are soluble means this silver nitrate is actually Ag plus and NO3 minus. So what we have here is a common ion. Can you tell me what the common ion is? Someone who I will not pick on. Bailey, what's the common ion?
Silver Ag.
Very good. Okay, so there's two sources of silver. All right, what's one source? Okay, one source is S. Okay, what's the other source of the silver? The second source of the silver is the common ion, the 6.5 times 10 to the minus 3 molar silver nitrate, okay, which is silver ion and nitrate. We don't care about the nitrate. Okay, it's called a spectator ion. And then what about the Cl? Plus S, okay? Is everyone okay with this, what I'm doing here? Okay, what's the common ion? As Bailey mentioned, the common ion is silver, Ag plus. Two sources of Ag plus. One is the 6.5 times 10 to the minus 3, and then the other one is the AgCl going back to Ag plus. All right, let's plug this into our KSP. KSP is 1.6 times 10 to the minus 10 equals S plus 0.0065 times S. All right, here we'll assume S is small, okay? Okay, so S plus 0.0065 is 0.0065. Okay, so this makes our life a little bit easier. 1.6 times 10 to the minus 10 is equal to 0.0065 times s. Right, so you're going to do this type of pipeline on the exam for the common ion. Okay, 1.6 times 10 to the minus 10 divided by 0.0065 equals s. And what do we get for s here? I think I'll use my calculator. No, I will not. How's that? 2.5 times 10 to the 8 molar. Okay, molar. All right, so the solubility of Ag plus is going to be S plus 0.0065. And that is 2.5 times 10 to the minus 8 plus 0.0065. And I want to convince you it's just 0.0065. 10 to the minus 8, 2.5 times 10 to the minus 8 plus 0.0065 is 0.0065. Okay, this is so small. 0.0065 is so much bigger. It's essentially 0.0065. Okay, so all of it is coming from the silver nitrate. And then the solubility of Cl minus is just S. And we calculated that S to be 2.5 times 10 to the minus 8 molar. Okay. So the presence of the common ion will decrease solubility. Okay, we just did this earlier in class. Solubility of Ag plus and Cl minus is 10 to the minus 5. In the presence of the common ion, it's 10 to the minus 8. Okay, common ion will decrease solubility. All right, our final thing in this chapter, all right, pH and solubility. So I think this is kind of interesting. You may like this. So magnesium hydroxide is a sparingly soluble solid. Okay, it has a KSP of, okay, whatever the KSP is. Now, this OH minus, what is OH minus? Is it an acid or a base? It's a base. So what happens if I add base to this? Okay, what do we know from Le Chatelier's principle? What if we add base to the OH minus? We add, I'm so sorry. What if we add base to this? If we add base to this, it's going to shift this way, and we will make more solid. Remember? Okay, so adding more base shifts the equilibrium to the left. Okay, you make more magnesium hydroxide. Okay, imagine you work for a chemical company where they want you to make magnesium hydroxide, tons of it. Just add a lot of base. Okay, raise the pH. Now what happens if we add acid? Okay, acid is H+. It could be a strong acid or a weak acid. What if we add a source of H+? Okay, what will that H plus do? Okay, this H plus will actually neutralize the OH minus. Okay, so H plus plus OH minus is water. So we will neutralize this, essentially making water, removing it. So where will the reaction shift? Because this H plus removes this OH minus, acid neutralizes base, and you remove this, so where will the reaction shift? Okay, remember Le Chatelier's to the right. So here we dissolve the magnesium hydroxide. Okay, so imagine you work for a company and they don't like this magnesium hydroxide in the whatever. Okay, how do we get rid of it? Add acid or lower the pH. Okay. So for magnesium hydroxide, with its KSP and sparingly soluble solid, you can add acid, lower the pH, and dissolve it. Okay, I think you guys did this in the Le Chatelier's lab. I don't know if you remember this 2-3 weeks ago. Add acid, you dissolve the precipitate. Make more precipitate. How do you want to do that? Add more base. Okay. So yeah, pH and solubility. Okay, so that is a wrap of all the things for test 3. Never thought I'd get to the day when we'd actually finish it. So I have 10:35 here. I got 10 more minutes. So we'll review Thursday. I'll bring a practice test over, so make sure you come to that or listen to the lecture. I got one. I'm going to start a little bit on chapter 17 on thermo. You can relax or a little bit here. Well, relax, but not relax. Okay. Let me just go over chapter 17 just a little bit, just 10 minutes, and I'll let you don't have to take notes if you don't want to. But so actually, we have a thermodynamics class at Methodist. All chem majors have to take it. It's taught by Dr. Fung. It's like a 4,000 level course. It's one of the highest chemistry classes we offer. And in chapter 17, we have a whole chapter dedicated to thermodynamics. So what is thermo? Thermo is the reaction energetically favorable? Okay, we're talking about in terms of energy. Okay, we are talking about it in terms of energy. So there's 3 thermodynamic parameters. Okay, there's 3 of them. One of them is something that we already covered in Chem 1. This is enthalpy. Do you know what enthalpy is? Remember I told you don't forget anything from Chem 1? Did you forget this, Bailey? Enthalpy. Okay, enthalpy means heat flow. Okay, I'm sure you remember it now, right? Heat flow. Heat flow. Okay, so enthalpy. Oh, what is this? Okay, enthalpy means heat flow. Okay, heat is usually symbolized by Q. Okay. All right. So heat flow. If your delta H is negative, okay, in joules per mole or kilojoules per mole, okay, we call that an exothermic reaction. Okay, which means it liberates heat. This is a favorable reaction. Usually reactions that give off heat tend to favor the products. Okay. And if your delta H is positive, okay, this is an endothermic reaction. Okay, instead of liberating heat or giving off heat, this requires heat. It must get heat from the surroundings. So that's parameter 1. Okay, parameter 2 is something that we have not covered. Okay, this is something from Chem 1. Parameter 2 is something called entropy. Have you heard this term entropy before? So this entropy can be S or delta S. Entropy. Okay, so enthalpy is heat flow. Entropy is disorder. All right, how do I describe disorder in the last 5-6 minutes of class? Okay, how do I describe disorder? Can I pick on? Okay. Did you clean your room? Everybody clean their room this morning? Okay. What happens after a day? Okay. What about your dishes? Did you wash your dishes last night? I know I did it. It was a mess. Or we did it. Okay. Did you wash your dishes last night? Okay, let's say you did wash your dishes. What will the state of your kitchen sink be by the next night, tomorrow night? Okay, it will be the same, okay? So it seems like things tend to gravitate towards disorder. So in this context, okay, you clean the kitchen sink, it looks so spick and span, nice and neat, you feel great about yourself, and then 2 days later, what? Okay, it's a mess. You clean your room, you feel great, there's no clutter, there's no dust, there's no dirt, everything is going great. What happens the next day, or 2 days, or maybe after a couple of hours, if you have children? Back to the same old mess, and it just, irks you. Okay? So this is the idea behind entropy. There is an increasing disorder. Things just happen by itself. Okay, so when things just happen by itself, we call that spontaneous. Okay, spontaneous. Let's say I release a gas in this room. Okay, let's say I take helium balloon and I release the helium from the helium balloon. Okay, can I get that helium back into this balloon? Okay, so helium release from a balloon or any type of gas molecules that you open up, okay, they diffuse, and that's spontaneous. Okay, so spontaneous means it just happens on its own volition. Okay, cleaning the kitchen sink, next day it's a mess. Cleaning your room, releasing a gas. Okay, the gas don't come back. Okay, I don't know. What's another example? You have a bird, you release the bird won't come back to your hands, okay, a pigeon, okay? So happens on its own volition. All right, so here, if your S is positive, okay, that means there's a tendency towards more disorder. Now, you have to recognize S and delta S. You can see an S. In thermodynamics, you can see a delta S, change in S. Here in enthalpy, it's just change in enthalpy from products to reactants. So if your S is positive, you're tending towards more disorder. So more spontaneous. Okay, if your delta S or S is negative, that is more order. Okay, so this is tendency towards more non-spontaneity, more non-spontaneous. Right. So which is more disordered, solid, liquid, or gas? What do you think? Which do you think would have more disorder? Solid, liquid, or gas? Which do you think occupies more space? Which do you think it's hard to just get back, corral, get back into where it needs to go? Gas. Okay, which do you think is second most disordered? And solids tend to be very ordered. Okay, just look at a solid under a microscope. All the atoms are arranged like a lattice, nice and neat and organized. So a gas has more disorder than a liquid, which has more disorder than a solid. All right. So all of these come together in number 3, and that is the final judge, which is delta G. This is called Gibbs free energy. Okay, so they all come together in this equation, whether a reaction will go to products or not. This delta G takes input from enthalpy, it takes input from entropy, delta S, and yes, sometimes you can force a reaction to go to products if you increase or decrease the temperature. So every reaction has an enthalpic component, enthalpic, and every reaction has an entropic, entropic component, and you can manipulate those with the temperature. The final judge is delta G. It takes input from enthalpy. It takes input from entropy. And if your delta G is negative, you are favored towards products. And then if your delta G is positive, no. Okay, your free energy does not favor products. You need to add energy to make it go to products. So delta G is minus. Okay, we're looking at a reaction that favors products energetically. This is all about energy. And if your delta G is positive, it does not favor the products, it favors the reactants. It doesn't go to products. So this is the final judge, it's delta G, and I am out of time. I'll see some of you in the lab on today at 2 o'clock. Okay, so please come ready and prepared. I think you should be able to finish in 30 to 45 minutes if all goes well.